First we turn to chromatin compaction. A chromosome is made up of heavily packaged DNA. Prokaryotes go through supercoiling, but of course, as eukaryotes, our process is much more complicated. Chromatin is DNA plus all the packaging proteins. Chromosomes are not always at the same level of compaction. During interphase, chromosomes are more relaxed because they are being replicated or being checked. In the M phase, the chromosomes are at their tightest because they are being prepared to divide and the chromosomes will be dealt out. After DNA, our next level of compaction is the nucleosomes. Nucleosomes are made up of histones. There is the H2A, H2B, H3, and H4 proteins, which form an octane around the DNA and the histone. The histone is positively charged, causing the negatively charged DNA to be attracted to it. The DNA will wrap around the histones to form a nucleosome. As the DNA creates a string of nucleosomes, there will be linker DNA between the nucleosomes. These histones, it should be noted, have protein tails. The next step of compaction is forming our 30 nanometer fiber. This is where the H1 protein from the histone comes out to play. H1 can be called the linker histone. H1 will cause the nucleosomes to twist around in a 90-degree angle, forming a thicker string of beads. Imagine twisting around a string of pearls. The 30 nanometer fiber will eventually form the 1000 compact mitotic chromosome. Unfortunately, we're not too sure how it gets to this way, but it just leaves more to discover. And here we have our pathway. As you can see, there's the DNA, the histones, the nucleosomes, a supercoiling with a 30 nanometer fiber, and then finally, our chromosome. Now let's move on to chromatin remodelers. These complexes use ATP to move the nucleosomes in order to access the DNA, since the only DNA they could access is the linker DNA. They physically move the nucleosome. Some of the examples are the SAGA and the SWIF-SNF, spelled SWI-SNF complex. Another strategy uses the histone tails. The tails contain positively charged lysine to keep the negatively charged DNA attracted to it. The histone acetyl transferase, or HAT, acetylates the histones, causing the DNA to loosen because the histone now has a neutral charge. This makes the DNA more accessible. The histone deacetylation complexes deacetylate the histones and restore the positive charge back to the histone. This causes the DNA to lock in because of the charge affinity. Histone modifying enzymes are highly regulated and finely balanced.